So today we are going to look on the wave equation. Before we proceed further in the wave equation, you will be asked to find the function of motion of maybe an elastic material. It can be a string or a spring or another elastic material that has been set to oscillate or has been set to vibrate at a constant velocity. So here we are going to use this example to show the processes and the steps of solving a wave equation. So if you have a stretched string of length 20 cm, it's set to oscillate by displacing its midpoint at a distance of 1 cm from its rest position and releasing it with 0 initial velocity. Solve the wave equation, this one, where z squared equals to 1 to determine the motion represented as the function u of x and t. So in general, a wave equation is written as d squared u over dx squared is equal to 1 over c squared times d squared u over dt squared. So generally, this is the wave equation. So this is what we need to solve given now specific conditions according to the requirement of the equation. So we're going to solve this equation step by step as we illustrate the processes in forward. So let's look at it. So graphically, this is how we can present this information. Yeah, this is the midpoint. This is 0, this is 10, and this is 20. So and this one is the maximum displacement from the point of position. Notice what we call the amplitude. Right, so this is how we can present this information graphically. So we want to go just step by step so that we can see how we solve this. So let us go to step 1. So our first step is to list all the boundary conditions from the data given. We want to identify these boundary conditions. So first, motion at the fixed points is 0. So that is u. And u at the point so this is the motion at the fixed points. So next, so we now assess the deflection. So between 0 and 10, it is given as x over 10. Between 10 and 20, it's given as 20 minus x over 10. So the third thing we consider is now the initial velocity. The initial velocity is given as, this is now the initial velocity. So next, so let our function u be represented as x times t. So we have, if we take the first derivative of u to x, we have this, and if we take the second, so the same case, if we take the derivatives of u with respect to t, we have. So now, getting back to our wave equation, it was represented as, so here the condition was that c squared was 1. So therefore, that means that, so now by replacing or substituting these values respectively, we have, so the next step is for us to rearrange this equation so that we can be able to separate the variables. So we will have, so since these two sides are just equal for the variables, we can just equate them to a constant k. And this constant k, we can present it as LP squared Yeah, so that it presents an oscillatory movement or motion. So by now rearranging these equations, we have, so here now we are going to find the value of x and the value of t. And now this now takes us back to the ordinary differential equations when we were learning about solving these ordinary differential equations. So we remember that when we had an ordinary differential equation of the form, yeah, so its general solution of y was found to be a, so this is the same principle that we shall apply, because if you look keenly, this is the form of this equation. So therefore that means that our x will be given us, and our t also will be given us. Yeah, so now substituting these values of x and t in our equation, which was u is the product of x and t, then now we have as this. So remember, this is now our general solution. Okay, so now let us proceed. But in the wave equation, we normally assign the constant lambda to be equal to the product of c times b. But now here, our c equals to 1. So meaning our lambda equals to b. So substituting this value in this equation, we have, so we proceed. We now want to find the values of these constants from the boundary condition. So the boundary condition number 1 is that the motion at this fixed point where x is 0 is 0. So representing, applying this boundary condition in this equation, we have, so therefore we conclude that a is 0. And so our equation at this point, u x t will be now, so the second boundary equation is that the motion at the other fixed point where x is 20 is also 0. So applying this boundary condition in this equation, we have, so that means that b is equal to 0. But then b will not be equal to 0. So therefore, with this sign 20 lambda, which can be 0, and sin x is 0 if x is n pi. So when x is n pi, where n is, then the sign of that number is 0. So therefore that means that 20 not really, but n will be a series of even numbers. So when n is a series of even numbers starting from 0, then we will have the sign of that number to be 0. So substituting for lambda, we have n. So getting back to our equation, we have, yeah, so these new constants are expressed as, and q is, so now we want to find the eigenvalues and functions from these equations. So generally for lambda, its eigenvalue is given us, and this eigenfunction represent that u. Yes, this is the equation. Similarly, where alpha or lambda is n pi over 20, which is similarly substituted into this equation. So the next step then is to find the eigenvalue and function of lambda number r. So actually, this is not lambda, but then n. So for r, this eigenvalue will be expressed as, so lambda r equals to r pi over 20, and therefore this eigenfunction is represented as, so then here in the wave equation, now our function x u x t now is represented as which can be, yes, this is the general form now. So in the next step now we apply the other boundary conditions. So this was the second boundary condition set. This was the second set of the boundary conditions that represented deflection. So when we apply this boundary condition to this equation, so this means when there is no deflection, I to 0. But now here BR is expressed as, so B is expressed as 2 times the mean value of x sin r by x over 20 between x0 and x20. So that means that BR so this what the condition you get, that between 0 and 10 this is the function, and between 10 and 20 is the function. So this is the same one. This is x over 10 because it is between 0 and 10. This 20 minus x over 10 because it's between now 10 and 20. So here now we want to carry out integration by parts. So let our I1 be this and our I2 be this. So we know that according to the integration by parts, we know that we have equals to so that is the formula for the integration of parts. So if we want to now find I1, so let our u be x over 10 and our dv be sine. So here we find du, which is now found by differentiating this equation, find 1 over 10, and now our v is found by integrating this equation. So we find it to be, so therefore we can write our I1 to be so 20 times 1 over 10. So putting in the boundary conditions, replace it. So this is 2, and finally we have it today. This one. So similarly, by integrating by parts, we have I2. We have it here. So replacing it in our equation, then BR, which is the sum of I1 and I2, we have, then we have it as this one now. So proceeding, if R is in integer 1, 2, 3, then BR is 8 over R squared sine r pi over 2. So let us try to prove. So if we let r to be 1, we will have 0, 0, and 0. So it clearly shows us that when r is in the form of 1, 2, and 3, it eliminates cosines and sine r pi. So we remain with 40 r squared pi squared, this one and this one. So that's what we remain with. So it remains to be 10. So therefore BR equals to 8. So now this is our BR. So coming back to our equation, it will be so this was our equation. So we are now going to substitute for BR in our equation. So it becomes, so this is now our equation. So applying the other boundary condition that goes to 0 and u. So applying this boundary condition to this equation, we find here now we want to differentiate this equation with respect to t. So every variable that has t, we differentiate, and every other variable that do not have t, we take it as a constant. So yeah, this one is a constant, but this one, that's a variable t. So we multiply it by minus sine so this one also has a variable t. So we differentiate it to be q r into r pi over 20 cos r pi t over 20. So here now, replacing t equals to 0 and the ut is 0, we have 0 equals to have this. So therefore we can conclude that qr equals to 0. As this after replacing qr with 0. So we can now simplify it that yes. So that this is now the solution, or the equation of motion, that's spring. So that is, this is the wave function, and we have solved it using the various methods, the relation by parts, the Fourier series knowledge, and such like. So subscribe to our YouTube channel, and always comment and share to your friends. Yes, so this is the DMM tutors, the best local tutors so far. Thank you for watching.